All right, cadets, settle in. Welcome to your systems deep dive. Now listen up, because today we are dissecting a fundamental skill every single professional pilot has to master: mixture control in piston engines. What we cover today, well, it's not just for some exam. It's for the flight deck and, even more important right now, it's for your technical interview. Get this wrong and I promise you, you will not get past the first round.
Because, when you're sitting across from that chief pilot and they lean forward and ask you to explain engine management, your understanding of this little red lever right here, that's going to be the difference between a job offer and a polite thank you for your time. This is all about demonstrating professional airmanship before you even touch the simulator, so let's make sure you are ready.
Okay, let's get right into it. We're going to start with the core principle. The mixture control is not just some secondary knob you fiddle with. No, it is a primary tool for managing the health of your engine, for maximizing its performance, and for ensuring peak efficiency. If you mismanage it, you risk everything from just poor performance all the way to catastrophic engine failure. But if you master it, that's when you demonstrate true command of your aircraft.
At its heart, this is all about one thing, and one thing only: the air/fuel ratio. Now, look at the critical words here: by weight. We are not talking about volume, we're talking about mass. We are managing the precise weight of air versus the precise weight of fuel that's going into that combustion chamber. This ratio, it dictates absolutely everything that happens inside that engine.
So let's build a bridge between theory and practice. You see, there's a chemically perfect ratio, and then there's the operational reality of flying an airplane. In a lab, the ideal ratio is one thing. But up in the cockpit, trying to operate at that ideal can be completely disastrous. Understanding why is absolutely non-negotiable.
So here's the number right out of the textbook: 15:1. That means 15 parts of air to 1 part of fuel by weight. This is what we call the stoichiometric, or the chemically correct ratio. And in theory, it's beautiful. At this ratio, every single molecule of fuel combines perfectly with every available molecule of oxygen. There's no waste. It's perfect combustion.
So you're probably asking, why don't we just fly at 15:1 all the time? Well, because perfection has a price. This chemically correct ratio produces the absolute highest possible combustion temperatures. And heat is the enemy of a piston engine. This kind of extreme heat can lead to detonation. That's an uncontrolled explosion in the cylinder, not a smooth burn, and it can literally destroy an engine in seconds. And because of that danger, we operate in two practical regimes, on either side of that dangerous temperature peak. For high-power settings like takeoff and climb, we operate on the rich side, around 12.5:1. We are deliberately feeding the engine more fuel than it can possibly burn. Now that excess fuel isn't wasted. As it vaporizes, it acts as a really powerful internal coolant. Then, for lower power settings, like in cruise where we're generating less heat, we can safely operate on the lean side, maybe around 18:1, and prioritize fuel efficiency. This graph right here, this is your Rosetta Stone for mixture management. It visualizes the entire concept we're talking about. See that peak temperature? That corresponds to that dangerous 15:1 ratio. Over here, to the left, in the rich range, that's where you have takeoff and best power. And way over on the right, in the lean range, that's where you find your best economy and your best specific fuel consumption, which just means the least amount of fuel you burn for the power you're producing. I want you to memorize the relationships on this graph. All right, enough theory. Let's put this into practice. We're going to walk through exactly how a professional pilot manages the mixture lever through the 4 main phases of flight. We're going to examine these 4 very distinct phases of flight. Each one has a totally different power requirement, and because of that, a totally different mixture philosophy. Okay, starting the engine, especially a cold one, we need a rich mixture, and the reason is just simple physics. Cold fuel does not vaporize easily. So by shoving an excess of liquid fuel in there, we're making sure that there's enough vapor present in the cylinder to actually mix with the air and create a charge that will ignite. Takeoff. This is the moment of maximum stress on your engine. We go to full rich, a ratio of about 10:1. Now this does 2 things at the same time. First, yeah, it gives us maximum power. But second, and honestly, more importantly, it provides maximum internal cooling from all that unburnt, vaporizing fuel. This is absolutely non-negotiable for protecting the engine. Now, during the climb, power demand is still really high, so we maintain an enriched mixture, maybe around 11:1. The logic here is exactly the same as takeoff. We are prioritizing engine health and preventing detonation by using that extra fuel as a coolant while we're demanding high performance from it.
So once we finally level off at our cruise altitude and pull the power back, the mission changes completely. The priority is no longer maximum power, it's maximum efficiency. This is where we lean the mixture significantly, to a ratio somewhere around 18:1. And look, this isn't just about saving a bit of fuel on one flight. A pilot who consistently and correctly leans the engine extends its life, reduces maintenance costs, and frankly, shows they're a true professional.
So how do we actually achieve this precise leaning in cruise? We don't guess. We don't use some old rule of thumb. We use our instruments. Specifically, we use the EGT gauge. This is the tool that gives us a window, a direct look right into the combustion chamber. The exhaust gas temperature, or EGT gauge, is your single most important instrument for setting mixture accurately and safely in flight. It gives you a direct indication of what's going on in the combustion process by measuring the temperature of the gases as they leave the cylinder.
So imagine you're flying. As you slowly pull that mixture lever back, you're reducing the fuel flow. Now watch the EGT gauge, it will start to rise. Why? Because the air/fuel ratio is moving closer and closer to that hot-burning, chemically correct 15:1 ratio. The temperature will keep rising until it hits a maximum value, we call that peak EGT, and then if you keep leaning past that point, it'll actually start to drop again.
That highest temperature you see, that is peak EGT. And I need you to understand this. Peak EGT is your landmark. It's your signpost. It tells you precisely where that 15:1 ratio is. It is a reference point that you find, but it is not, I repeat, not a target for continuous operation. Once you find peak EGT, you will then adjust the mixture, usually by enriching it just a little bit, according to the aircraft's pilot operating handbook. Okay, before we get to the interview practice, just one final, critical reminder of the consequences. Getting this wrong isn't just inefficient, it's incredibly dangerous.
You see, running the mixture too lean for a given power setting creates a whole cascade of failures. It starts with overheating. That leads to power loss. Then, the slower combustion can literally burn and warp your exhaust valves. And ultimately, this can all lead to the most destructive condition of all, detonation. This is exactly why precision is not optional. All right, this is it. You're in the chair. The interviewer has finished the small talk, and now it is time to demonstrate your technical knowledge. Let's practice. So they ask a broad, open-ended question like this. They want to see how you structure your thoughts. They want to know if you really get the core principles. So, how do you respond?
Your answer has to be concise, accurate, and professional. You state the operational requirement, you identify the limiting factor, and then you explain the solution. Something like this. For takeoff, we require maximum power, but operating at the chemically correct ratio of 15:1 would create dangerously high engine temperatures. By enriching the mixture to approximately 10:1, the excess, unburned fuel vaporizes, providing an essential cooling effect that protects the engine during this critical phase of flight. See? That answer shows complete comprehension.
Okay, next up, they'll probably give you a practical scenario. They want to know you can actually apply the theory. They want to hear your procedure. Here is how you nail that answer. Describe your action, your observation, and your final procedural step. For example, as I slowly lean the mixture, I'll observe the EGT rising as it approaches the chemically correct ratio. I will identify peak EGT and use that as my reference. For best economy, I will then enrich the mixture slightly, as specified in the POH for our cruise power setting, to ensure I gain fuel efficiency while maintaining a safe temperature margin. Referencing the POH there, that's critical. It shows knowledge and it shows operational discipline.
So there you have it. The theory, the application, and the interview questions. You have the knowledge now, but the final question, that's not for me to answer. It's for you. When you are in that seat, how are you going to demonstrate the mastery that proves you belong on that flight deck? I want you to study this material until it is second nature. That's all for today.